Hi, everybody out there in internet land and to the MIT students as well. So welcome to this week's Julia Computational Thinking class. So we had a lot of fun putting together this notebook over the weekend. So today's lecture is going to be nominally about transformations, but maybe I'll do a quick sound check. Can I be heard?
Yes, loud and clear.
All right, great, thanks very much. But in addition to talking about transformations and various mathematical subjects, we will also talk about composability in mathematics, composability in computer science, composability of software is a big topic. But let me start by actually playing with what's in this notebook. So we did a little bit of this last Wednesday, but I think it's fun just to start playing. And so you can go right here to the fun stuff. You could click on the table of contents if you like and play with any transformation that you would like. Let's just start with that. So I'm labeling the transformation with a t and a superscript -1 for t inverse. I'll explain a little bit later on why that might sound backwards, but there's a reason why we're going to call it t inverse and not t. So I made it that everything you need is can be seen in one window. So you might want to, let's see here, let's just make it depends on how you resize it, of course. But here, let's maybe make it smaller so you can see the big picture, and then I'll make it larger so we can zoom on in. Let's see, so you've got the grid lines, which is actually being added to the original image and the processed image. We can kill this thing right here, give you a little more room. We've got a zoom that is scrubbable, so you can sort of zoom in, zoom out. With this right here, we've got a nice pan here.
Can you zoom in on your notebook?
Well, I was going to do that.
Oh, you can't.
I was going to do that in a moment, but I wanted.
Same problems.
Yeah, I wanted to also be able to reveal here. Okay. So just a quick thing just to show you how to use this, panning. Eventually, we might want to just do this with a mouse, but this isn't so bad. And this works with Pluto, that you can zoom in the X direction and the Y direction just by grabbing and this scrubbable. Okay, and you've got these parameters. Right now we're just applying the warp, so you can you can kind of bunch up the poor corgi or leave them in good shape. Okay, and of course you could put any picture you like. All you have to do is replace what's in quotes here with whatever particular, with whatever picture off the internet you like. Or of course, if it's on your computer, all you have to do is just load it, the file name. So you get to play with all this. And what's wonderful is this entire notebook is completely self-contained. So however this thing works, it's entirely in this one notebook. And there's something very magical. Many of the students from previous semesters really enjoyed this, that you put together something from beginning to end. You feel completely in control. In other courses, maybe some of you might have taken, that people will give you sort of like 80% of the code, and you're supposed to fill in the missing parts. And I understand the reason why people do that, but you always feel a little bit out of control. Like, what is it that's there that you didn't understand? So the entire code for this is completely here. And let's just play with some of these functions before we delve in. And so I've got a number of functions. You can actually click on these linear transformations if you want to see a few of them. We have things like scaling and flipping and rotating and shearing. These are the linear transformations. We also have a bunch of nonlinear transformations. Translate is technically nonlinear, though it feels linear, because the definition of linear requires 0 goes to 0. So in general, translate moves 0. We have this nonlinear shear that we're going to play with. The warping is clearly nonlinear, and some other nonlinear functions. Here are a couple of others we made up and we played with. So I would like to encourage everybody to kind of make up a function and just see what it does. And again, in years and years of math courses, people would draw a little diagram. Maybe they would just see what happens to a square. Maybe there'd be a curve. I guess with plots, you can maybe more clearly see where the contours would be. But I like images. I love, honest to goodness, real images. I think there's nothing like them for building up an intuition as to how transformations really, really, really work. So
just to emphasize that we are sort of taking each pixel as representing that particular point on the plane, and we're seeing for each pixel, how does that move around?
yeah, if I could, I would actually zoom in on a pixel. Let's see if I can. I can actually. Oh nah, I mean, I'd be kidding myself if I told you I could see the pixels now. I don't know. Let's see if we can get a little closer. Even trying to zoom in some more. This is about as far as I can go. I do almost think I see. Yeah, I see the pixels. They're like little
Yeah,
rectangles. I don't know if you could see them over my
yeah,
zoom,
you can see.
but you see them as well.
Yeah,
Yeah. So
pretty
so
much.
and actually dealing with pixels adds a small complication. It's not conceptually harder, but it adds a small complication than just dealing with pixels are discrete as opposed to sort of the continuous curves as they might be presented in a mathematics course. So you just have to deal with that, but it's worth it, I would say, because you get these nice pictures. So if I may continue to play with some of these, just like I was in Photoshop or something, but this is better than Photoshop because I've got control. I know exactly how these functions are defined because they're just somewhere down in the notebook. All right, so I will zoom in here, and just I want you to do this with me. I don't want to just do it for my own fun. I mean, I could do this all day, mind you, but rotate the corgi. There we go. So this is rotating the corgi. It's just taking this parameter alpha and just rotating it around, and it's pretty fast, I would say. So there's the rotate. I could instead play with shear. Again, you can make up your own function anytime. So here's the shear function, and what shearing does is it kind of bends the parallelograms, if you will, okay, until they're almost unrecognizable, if you will, right? We can go the other way with shearing. So there's shear.
The horizontal lines stay on the same horizontal line
That is true.
with a shear.
That is absolutely true. We can now do. We could actually define the transformation with any matrix, and for that, this is where the matrix over here applies. And maybe I'll just go down a little bit. Feel like there's a lot of wasted real estate here. I know Dave's going to want me to zoom in, but I want you to be able to
You
see
can move the matrix down next to move the matrix cell down next to the picture.
I could, can't I? That's true. Except that I always mess this up. Let's do that. Let's move the matrix down. Here we go. That's not a bad idea, actually. Okay, then I can zoom in. I keep forgetting that this thing is infinitely flexible, right? Which is actually good to keep in mind. So here we're applying the matrix, and I like to argue, and you'll see more about this in the notebook, that in a way, this transformation is the matrix. And so I don't like to think of matrices as just arrays of numbers. I like to think of it as linear transformations. And if you want some intuition as to the various different kinds of transformations that are available, you can just play with the different elements of the matrix, and you'll see that what it does, to the point of when you get these parallelograms that are sort of big and needle shaped. I don't know what the word is. You can't even recognize the picture anymore, right? But again, you could play with this a little bit and see what it's doing. But one thing for sure with matrices is that a grid of rectangles will become the lattice of parallelograms, right? The grid of equal-sized rectangles becomes equal-sized parallelograms. And this is, in my mind, truly the action of a matrix, right? Not a bunch of elements, but literally this transformation of a corgi or whatever other image you're playing with. This is really how I would like everybody to think of matrices, and not just as tables of numbers. Okay, so we'll say a little bit more about that, but let's just play some more. So the symbol here, and it's I mentioned it later in the notebook, but just to kind of preview right now, the symbol means compose. It means that you're going to shear with minus alpha. Look, I could do these out of the way now. So let's put that back out of the way. Okay, so this says, it goes from right to left. It says shear minus alpha and then shear alpha. And you'll notice that it doesn't do anything. So no matter what I change alpha to, this operation and this operation cancel each other out. We say that these operations are inverses of each other. Okay, so that's coming in this lecture as well. Let's play, why don't we just play with a nonlinear shear, just as, since everything we've done right now has been linear, let's see what a nonlinear operation might look like. So here's a nonlinear shear, and there's something parabolic. We could actually look at its definition here, but these are actually parabolas now. But what I'd like you to notice is that if you just look at sort of a small section, it's still just a bunch of rectangles, right? They're slightly curved and they're warped, but if you get smaller and smaller, in a small patch, everything is kind of almost linear. And so much of applied mathematics is based on the fact that if you look in just a tiny little region, if I made my original rectangles smaller, or if I drew more grid lines, you would see lots of, here, I guess I could pretend to draw it. I mean, I guess I could really draw it, but why don't I just pretend to draw it because it's easy. So, I mean, I think it'd be easy to just sort of imagine what it would be like if there was a grid line. I'm just doing this freehand, so don't take, oh, I guess I can't do this very well. But you can imagine that these parallelograms, right, the smaller ones get more and more parallelogram-like, more and more like a linear operation. Okay, and like I said, this is what so much of applied mathematics is about, that if you just look locally, if you just look at a small region, every map looks linear. Okay, and in fact, before computers, that was kind of like the only game in town, really, that pretend everything is linear and hope for the best was kind of the most analytic techniques before computers were invented. Okay, so that was the big game in town. It's still a bit of a game. Okay, some other nonlinear transformations that I had, I showed you this last time, but I'll kind of, you can play with them again. I have the polar to XY, which is kind of crazy. I mean, the corgis are kind of ripped to shreds and put in different places. The other one that I had was the R theta one. So that goes the other way, and you can see the sort of fanning out. And I'm hoping you're playing, you're playing along with me. But if you put the two together, actually, let's do it the other way first. If you put the polar coordinates to XY and then go back round trip again, you'll see we come back with the original picture. And so going to polar and going back to XY coordinates is they're inverses of each other. Okay, and here's one that I just made up just for fun. Again, you can type any function you want. Okay, it depends on this parameter alpha, so we can play with it a little bit. Whoops. What did I do? I scrolled. Okay, so let's see. I'm going to go down one level. Hope that's okay, David. Okay, but here, let's play with the alpha parameter. So when alpha is 0, nothing happens. But as alpha starts to get big, the poor little corgi gets scrunched and pulled, and I don't know what's happened to him. In fact, he gets doubled up, right? So that's kind of, so not all maps are one-to-one. So if you see, when I do this, look, this corgi has two heads. It looks almost scary. Okay, and what happens to the parallelograms, and you'll start to notice, I could zoom in now, you'll start to notice that these parallelograms are starting to get really messed up, like over here. What the parallelograms get squashed down to 0, and then here you could see they look really strange, right? And so this can happen to functions. These are called singularities. Okay, and they correspond to the linear approximation being really weird. Okay, and so here's some of the things to play with. I don't know. Before I move on, anybody have any of the functions that you'd like to see? I can do any function you want. So the functions are going from -1, 1 to -1, 1 in the x and y coordinates. So if anybody has a function, let's see if there's anything in the chat. Okay, nothing at the moment. But if anybody wants to just try a function, I don't know what'll happen. Dave, you got a favorite function you'd like?
What about something periodic like sine?
Oh, I have no idea. Let's try it. So
I guess it would be something like sine of 5x.
sine of alpha x, and we could kind of
yeah, good idea.
play with the parameter.
Sine of alpha x comma y, alpha times x comma y to start with, and then we can see
what happens. I've never tried that before. Okay, so let's see. So let's start with the alpha. let's see, this is, maybe I'll move the alpha down now that you taught me that I can just do that. Let's do that. Again, I hope you guys will be doing the same thing, but here, so, I mean,
Somebody,
if I guess I make it really periodic, do I want a large alpha or a small alpha to make it really periodic? Oh, yeah.
larger. Yeah,
Yeah, there we go.
nice.
Oh, gosh, that's so strange. That is,
Somebody suggested the Hilbert curve. I think that might be a bit tricky
you
to.
gotta give me the function.
Yeah, you've got to write down the function.
You gotta write it. You write it down. I'll type it in. I'll copy and paste it in. Oh, this is freaky. This is too freaky for me.
Okay, so let's make it freakier. Put a cosine in y.
Oh no. Cosine alpha times y with a 10.
Sure.
Okay, let's try that. Oh, I don't know whether this is.
That just doesn't work. Oh, but you need, yeah, you can put alpha back to 1, I guess, probably. Or
Well,
0.
I'm not even sure if alpha 1 is. Yeah, I don't know where it's
Who
going.
knows what's going on there?
Yeah, it's probably. Oh wait, I'm getting something here. Okay.
Basically, you can do arbitrarily weird things.
So white space doesn't mean it's broken. It just means that it's outside the window that we're plotting in. There's actually
It's because our original image is embedded in a white square.
Correct. So
that's quite cool, actually.
Yeah, you could sort of make a kind of tiling pattern or a mosaic this way. There we go.
And then you could mix it up. So you could, you want somehow 10 alpha times x times y or something.
Oh, I'm going to regret that.
That's going to be terrible.
I think so. No, I don't know if it's terrible.
Yeah, it's kind of nice.
Okay. Last chance for somebody to mention a function you'd like to play with. But this is, maybe I'll just make another pedagogical point where I've seen over the years, and maybe some of the students have seen this also, that professors make these demos. In the past, they were these Java applets, and you're limited to seeing whatever it is the professor wanted you to see. So they might have picked a few functions, but we think that you should be able to have any function that you could dream of. Just put it in, and have the full power and flexibility of a software language.
Also, often the way sometimes these applets have the ability to write your own function, but basically you're writing a string, and then that string somehow has to get parsed, get converted into an actual piece of code. But here we're just writing the code because we have this interactive notebook, basically.
Right. So it's completely live. Yeah. All right. So you get the idea. We have these. Let's go back to the identity just to kind of return everything back to normal. So we've got these images, and maybe now one more pedagogical note, if I may, and say, so you've been in this class now, we're up to the 3rd week, and you've been sticking with us, and maybe you're wondering, why are we doing image processing? Is this an image processing class? I mean, there are classes on image processing, and as you probably picked up on from me already, this is not an image processing class. The image processing is merely the motivator. We think that playing with images is just so much fun. What we really want to do is teach you this combination of computer science and math and Julia programming that I think could only be done in the way we're doing it. And so, and you'll see that the other modules that come up will have the same motivation. So the analogy I try to make in terms of, as we put this class together is, I think about the time I learned a foreign language. So I was a graduate student at MIT, and I took a French class at MIT. And I remember the textbook, the whole goal was to learn French. But you didn't just learn French. Chapter by chapter, there was a French construction, but there was also how to order a coffee in a cafe in Paris, or how to go to the post office, or how to do your laundry. I mean, all these very useful things, if you're in France. And you also learn things like the culture of France, right? And how people think about things, things that are different. So in a way, that analogy was what kind of stuck with me with, we want to teach Julia, but we want to teach it with an application, like doing laundry, right, or ordering a coffee. So the image processing becomes sort of the sort of cultural background, if you will, so that we can present learning Julia in a real life context. Okay. Otherwise, one ends up with these sort of what seems very dull to me, where here's a for loop, here's an if statement. I mean, I couldn't imagine to me anything more boring than what's a for loop and what's an if statement. Okay, so there were a few leftovers from the last lecture, and one of the folks, I think it was on the Discord, I asked, so what is a linear transformation? And there was an interesting wrong answer. I love interesting wrong answers. Interesting wrong answers are so much better than right answers. I wish everybody would always give me interesting wrong answers. So, so somebody proposed something like this, that if a transformation takes lines into lines and perhaps preserves the origin, then maybe that is a linear transformation. And I vaguely remember that when somebody said that, I wasn't prepared to completely agree. I don't know, maybe I'll go back to the recording and see what I really did. But I remember being not so sure about that this would be enough for it to be linear in the traditional sense. And for now, let's think of linear as taking those rectangles into those nice lattice of parallelograms. And we found this perspective map. I would love to implement it in Julia, but we took this one from the Khan Academy, and it shows that if you have like a nice set of rectangles on the floor and you look at it in perspective, some of you might know there's this concept that comes originally from art, the vanishing point, right? The parallel lines, when you draw them, all meet at a point called the vanishing point. And there's this nice demo, and I have it right here from the Khan Academy, so I'll bring it up. And again, I'd love to get this implemented in Julia. It probably wouldn't be that hard, but I thought I would just kind of show you. I'm gonna get rid of the hallway and maybe even the second vanishing point. And here you could see that I just love being able to move this. So these in the real world, in the real world plane, these green lines would all be parallel, right? And from different angles, you'd have a different perspective of how this would look. Okay, and right there, the second vanishing point here. Let's do like this. You can go like this. You can play with all sorts of things. So here, let's bring in the second vanishing point now. So the second vanishing point has all the diagonal lines, right? So those are, if this was originally a square or a rectangle, the blue lines would be the diagonal of the rectangles. And from this perspective, the red lines stay parallel, they're horizontal. But my key point is that all lines, not just the ones you see, but all lines here would actually be linear. And so this perspective, you can always make things the origin goes to the origin, so that's not a problem. And so that just goes to show you that lines going to lines is not sufficient for it to be linear. You won't get the nice parallelograms, right? Obviously, these are sort of trapezoidal or something, right? These are not quite parallelograms. They're certainly not congruent. Okay. By the way, for a quick argument, maybe it's worth doing this. For a quick argument as to why lines go into lines, if you have if you have sort of, here's your eyeball, right? How do I draw an eyeball? I don't know. Here's your eyeball, and you have a plane that you're projecting onto another plane. It doesn't have to be parallel, right? That if you have a line over here and you project it from the point, right? You create an intersecting plane, and there'll be a line over here, right? This is the image. So no matter what line you have in the real world, the plane between the line and your eye will create an intersection in the image plane, and that will, the intersection of two planes is always a line. So there's your quick mathematical proof. Okay, but thank you for whoever out there gave this nice wrong answer so that we can actually go and explore that. Okay, so what else is left over from a previous lecture? Let's see, what there, okay, we defined these functions last time, and I just wanted to say a little bit about style. So this is one of those things where if you're only concerned about correct code or getting the answer right, then you won't care about this. But if you want to be fancier and get the code to be more readable, then this is this is for you. So
you maybe zoom in again, please.
Gosh, it's so big to my eye, but okay.
That's good. Thanks.
It's practically now this like a PowerPoint like thing, which is probably the whole point. Right?
Yeah.
Like, so yeah, let's see. Could almost do this big. All right, here we go. Good. Good idea, Dave. Thanks. So 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 Philip's got some comments about here. Come on, Phil. I might have to close my door in a second. Hold on. Sorry, everybody. He's still pretty loud. Okay, so I'd like to ask each of you to look at, say, this line versus this line, and tell me which one is easier to read. I don't think there'll be much of a controversy. Oh, Charles asked a good question about perspective maps. I'll go back to that in a minute. I like your question, Charles. Yeah. Okay. So I believe you'll all agree that seeing X and Y, this X and Y thing, yeah, and one of the students as well just agreed that this is so much easier to read. Again, it doesn't matter from a mathematical viewpoint. You could index V of 1, V of 2. You can, you can write the indices. It'll work mathematically. It'll work computationally. But if you want to actually be a human and read these codes, there's no question that the second set is easier to read than the first. And so I made the choice to actually write them, the codes, the functions more like this than like this. There are a couple of other choices, but one might ask, why would I actually, this looks a little bit easier to read than this, though this one's not so hard to read. This, I'll remind you from last lecture, this is an anonymous function, which by the way, we've named. I always feel a little awkward saying, this is an anonymous function, but I've now named it. It doesn't feel like it's anonymous anymore, but this is an anonymous function, which has now been named f. And the reason to do that is these anonymous functions allow you to put in those parameters. And so it makes it really fun to be able to rotate by alpha or shear by alpha or warp by alpha. So if you go and look at the definitions of the functions, and I'll bring them back here with this table of contents. So here's my collection of linear transformations. You'll see that when I had a parameter, I used the anonymous function format. Okay, so so this function, scale x of alpha, will scale the x coordinate. When I didn't have a parameter, I just did it in the short function format. So these are in the short function format, but whenever I had a parameter. So this lets you put in the parameter. Okay, so that's why we would use the anonymous form. It makes that possible. So let me go back, if you will, to Charles's interesting question. So so this perspective. So the question is so Charles said, I thought perspective is a linear transformation. And there might be a reason, if you've seen these things somewhere, you can actually do this with matrices. But the funny thing is, if you want to do 2x2 transformations, if you've seen this somewhere, if you want to do 2x2 transformations for perspective maps, from R2 to R2, like we're doing in this notebook, you need 3x3 matrices. Okay, and in fact, if you want to do 3-dimensional transformations, you need 4x4 matrices. And what you do is you end up dividing by something. So if you look, you'll see that they've got linearity inside, but they're not linear. Okay, so to be linear, you have to have these parallelograms. I'll give the technical definition of linear in just a little bit, but intuitively, all of these have to be congruent parallelograms, which they obviously are not, right? This is a big parallelogram. This is a tiny little parallel. I mean, actually, it's not even a parallelogram. These two lines are not parallel. It's at best half a parallelogram, which is not a parallelogram. But these two lines are parallel. These are not, right? And that's big.
The trapezia, aren't they?
Is that the word? It's half a trapezoid. It's a trapezium.
That's just the British word for what we call trapezoid.
Oh, you got a funny word for trapezoid? Just like you pronounce the letter Z funny?
There's nothing funny about it.
I thought does a trapezoid have to be, I guess I'm thinking of isosceles trapezoids. I guess this is a trapezoid.
But wait a minute. I thought, the way you do it is you add one more, you add a constant term, right, to the vector, right? It's always x, y, 1 gets mapped with a,
right, those are homogeneous coordinates. That's right. That's how it becomes three-dimensional.
Right. But how is it, but isn't that a linear transformation? Isn't that why we do?
It's linear in xy1.
Right.
Okay, and then you have to somehow do something to put it back into the plane, right? So usually you divide, what is it, by the sum of the three numbers, I think. There's a division in there. And so the combination is technically, it's got pieces that are linear on the inside, but the collection is not technically linear anymore.
I don't think I knew that.
See? You learn something new every day. All right. I had fun working with Dave trying to find a good example of something that sends lines to lines, and I came up with all kinds of weird examples that would. We had other examples that. Oh, here, let me show you another example that we came up with, but it doesn't work. So here, just for fun, while we're at it, and again, this is maybe another thing about computational thinking, where you can do things with your brain, but you could also do things with a computer. And, I think wisdom is knowing, I know people in the math department would say you should always use your brain. And I guess I know other people who should say you should always use your computer. I think wisdom is knowing when to use what.
You need the X, Y.
I see it.
What does the comma notation after the vector mean?
Yeah, I wanted to hide that, but maybe it's to explain it. It's because I'm going to, it's a little bit of a obscure Julia thing that makes things work. So it's going to deconstruct a vector so that I could give it I want to be able to give it a vector and a tuple input. So a vector, I didn't really want to get into that, but a vector looks like this, and a tuple looks like this, and I want this to work on both. So it's a little bit.
I see.
So if you don't put that comma, it will define a function that accepts two arguments. But we wanted to define a function that accepts one vector, one argument, which we're going to use as a vector. So we're going to, as Alan said, deconstruct that one argument into those two values, x and y.
Gotcha.
Yeah. So this is advanced and not so important. But here, did I get this right? So, oh yeah, okay, this will work. Maybe I let's pour things upside down, but whatever. Here, let me maybe go.
Because you have the inverse.
Yeah, I know. Let's see if we can. I don't know. It's a little bit trial and error. The main thing I want you to see, though, is that this map, e to the kx, e to the ky, preserves horizontal lines and vertical lines. And so you might think, okay, maybe this is an example, but it doesn't preserve other lines, and one quick way we can check that is I could compose it with a rotate, right? So let's rotate it by, I don't know, whatever. What did I do wrong? What did I do wrong? Why can't I?
You need to put the whole nonlinear transformation in parentheses.
Parentheses is what I was going to say.
Oh no!
No, not there. No.
Oh, the
part that you wrote first. Yeah.
This part.
The whole thing.
The whole thing is a function. You want to compose two functions.
Exactly. No, not there. Before the rotate.
Oh, yes, I see now. Thank you. Okay, so it still looks straight.
That's because it's the wrong way around. You need to rotate in the other. You need to rotate.
That's the other thing, I guess, about doing things on a computer. You still have to make sure you do it right. There we go. Thank you. Yeah. So in fact, let's put the alpha over here, and maybe I don't even need the alpha over here. Let's just maybe get rid of it over here, and you can see that. Let's go -10. Okay. So you can see that these lines are anything but horizontal and vertical after rotating, right? And so it's easy to come up with maps where the horizontal and vertical stay horizontal and vertical, but other lines clearly get completely messed up. Okay.
I like the way that the lines get thicker.
You like that?
Yeah.
So zoom, because it's blowing up, right? I mean, there's some singularity here that it's heading towards. I don't know if I can pan it over a little bit, or no, I won't. Or can I see more of it? I don't know. So if I zoom in, will I be able to see more of it?
I think it's asymptoting.
Yeah, it does seem to be doing that. So this is one great way to discover all sorts of phenomena that you never knew functions can do. Okay, and what else did we have? The style. Okay, and then yes, the functions with parameters. Here's just an example with functions with parameters. Okay, so moving along in this lecture, we made up a bunch of linear transformations, and every one of these could have been just written with a matrix, but in some sense, it's not clear that you should write every one of these with a matrix, in the sense that sometimes a matrix is overkill. And those people who know me well know that I love linear algebra. So if they ever heard me say, sometimes a matrix is overkill, people would be surprised to hear that out of my mouth. But sometimes a matrix is overkill, like if you're swapping X and Y, or if you're flipping Y, it probably, you don't need a whole matrix for that one. In fact, none of these seem to really require a matrix. However, if you do want the general matrix, and you saw that happening, here's how you would write the general matrix. You could put in either the 4 elements, A, B, C, and D, and you get this is the matrix times vector, right? So you take this matrix times the vector X and Y, and you get you get AX plus BY and CX plus DY, or you can actually do the matrix times vector directly. And so this is another bit of fancy, Julia. I don't know whether I should explain it or not, but if you'll notice, what I did here was I defined a linear transformation of a matrix. Okay, I defined it as matrix times the so it'll take a vector into the deconstructed vector. Okay. Anyway, that's fancy, Julia. Let me just say that this just lets me.
You could just write that as V1, V, comma V2.
Yeah, but I kind of just made a whole point about not doing that, right? But I could have, right?
Well,
I could have. Right.
I mean, the point is that we've been using
the deconstructed form, and so we're going to keep it that format. Okay. So, okay, here's my nonlinear transformations, like the nonlinear shear that here's the warp, and the warp is actually nothing other than a rotate that depends on your position. So it's actually kind of nice to be able to write it in just that way. So the further out from the origin you are, the more you're rotating, and so that's why you get the big twistings as you sort of move away from the origin. Okay, here's the xy or theta. Here are a couple of other functions I played with, but here let's talk about composition. Composition is a big, important, simple but big, important thing. Okay, and so to talk about composition, let's just talk about composition of elementary functions for starters, functions of one variable. So here is a sine of cosine of x. Okay, here is the function that composes sine with cosine and evaluates it with x at the value x. And let's just x be some random number, and in Julia we could do this approximately equals, just in case there's a little bit of numerical, right? I mean, we could do equals, which would actually, it might be false, so maybe not. Oh, actually, in this case, there's no numerical round off. So I didn't need the approx, but whenever there's floating points, I just do the approx, and this way I don't worry too much.
That's because sine compose cos is just defined as
it's just defined as this, right? So it's doing the exact same thing, period. That's clear. So I'd like to emphasize, because this is the sort of thing that gets kind of a little bit confused even in math courses, the difference between sine and sine of x. the problem is in math, it gets very, very confused. So I'd like to sort of talk about this object in Julia, for example, or in math, and perhaps this object, right? So sine of x is a number, right? I put some number x in, and out comes the sine of x. Now, of course, this gets a little bit confused if I say f of x equals sine of x, and then, in math, and you might be talking about the sine function in math rather than the evaluation of sine at one number. We humans are so good at not worrying about it that we don't worry about it unless we're doing something on a computer. But on the computer, there is a function itself can be an object, like sin, sine, right? And that object exists whether you evaluate it or not. So if everybody sees what I mean. And so this is sort of a little bit of the computer science. It's also math. This thing is a function, sine. Okay, it's not been evaluated. It's just a thing, right? It could be composed with a cosine, and this thing now is a function. Okay? If I want to, I can go ahead and evaluate it, which I did over here. Here, on the other hand, this is. You see the difference? Here, I take a number x and I get a number out, cosine x. Then I go and get another number out, the sine of cosine of x, right? It never happened over here that there was this function never existed, sine composed with cosine, never existed on the right. It only exists on the left. Okay, so I don't know if that like bends brains or not. But
yeah, I have a kind of stupid question.
Oh, please.
So when you use special symbols, I can see you entering them. Is there a way, if I see the special symbol, of knowing, can you just mouse over it or something and have it tell me the?
Well, you could copy and paste it.
No, so that's a great question.
But the answer,
because I really don't want to have to go off to other pages if I can avoid it when I'm trying to program by example.
In most cases, it's the LaTeX thing. So you may already know it if you know LaTeX.
Yeah.
Is there a way, Dave, to actually know?
It seems to me like you should, when you mouse over it in Plato or something, it should just tell you.
That would be nice.
Here's
does it actually mouse over? Let's.
So
it might be. It does.
Maybe can you click there and open the live docs?
That's exactly what I was going to do. Is a prox. Oh, but that's not quite answering Charles's question.
If you go to the REPL, you can do it. Can you try opening the REPL and doing question mark and that symbol?
Well, then I have to change my screen.
The REPL is just in the terminal. The Julia, when you run Julia from the terminal.
Dave, that'll change my screen sharing. I'm only sharing this one browser. That'll mess me up.
When you moused over it, it would just tell you what the.
That's not a crazy idea. We should tell Fonz that. He'll probably implement it. So what we did get when we moused over is the name of the function. So
So do you want me to share my screen?
Sure.
Show that?
Why not? That'll be fun. Let's do it.
Just a minute. Can you see my terminal?
We do see your terminal.
Okay, so I just launched Julia, however you launch Julia from, and you get from, in my case, from the command line, or I could do it by searching for Julia, my Julia executable. And so now I'm running Julia on the command line instead of in Pluto, and I'm going to type question mark and then this this symbol that I don't know how to write. So when I type question mark, it actually, so this is the normal Julia prompt, and I can write Julia code here, like x equals 3, and what is x, and but if I type type question mark, it immediately changes the prompt into this help prompt. So we're now in help mode, and if I type the name, type this Unicode symbol, it actually tells me, the first thing it tells me is how I can type it in Julia.
But wait, can I then do it? Let me grab the screen back if I may.
Does that answer your question, Charles?
That definitely answers it in the REPL for Charles.
Charles, you are muted.
But can I go? Can I go?
I don't know how to do the same thing actually straight in Pluto.
Can I do it in? Doesn't the help?
Oh yes. No.
This is a Pluto problem right now?
I'm sure there is a way, but I can't think of what it is right now.
Yeah, okay, we'll find out and get it, and maybe even add the mouse over. I mean, there is something, I guess the other thing you can do is if you go.
Yeah, it would be nice if when you moused over, because whenever I read something, I want to be able to write it, right? And that's, if it's the translation's only going one way and it's effort to go the other way,
It's true.
and that becomes, you
So,
know,
as I just showed, that information is available in Julia.
Yep.
You just have to know how to get to it from Pluto rather than from the command line.
There's another thing you could do which doesn't answer Charles's question, but it's not a related question, which is I can go /:tab and see a list of all sorts of Unicode things, and you can pick one that you like. For example, you could take a cow and then hit tab, right? And
you get the emoji.
Yeah, and then you can go cow equals 2, and you can take the square root of your cow and all sorts of things. Yeah, so there's a list of fun symbols, and this actually comes in handy. For example, I saw the instructor in the math department, Christopher Kakis, he shows off differential equations, and there are lots of examples of differential equations where there are wolves and rabbits or something like that, wolves and rabbits. So, and everybody always goes W and R, right? But, Chris has a picture of a wolf and a rabbit. It's so much better to have that. It actually works for the code, so much better than the letters. Okay.
So apparently it does work in Pluto already if you click live docs and mouse over the symbol.
You're kidding me.
Can you mouse over the circ symbol?
Okay.
Yeah.
And
it does say there the symbol can be entered in the Julia REPL by typing /circ.
Oh, well, maybe you've got what you want. Let's see. So,
yes, I don't think it works with all symbols.
Yeah, it
my method
depends on how the help document is written, really.
Yeah.
So when I mouse over, that's not happening. I don't get that thing popping up on the right. How did you?
You got it. You see the live docs over here. You got to
click. I see. Hit live docs below there. I see. Right. Oh, okay. Very good.
Hide it and open it.
Excellent.
But yeah, we should definitely get for symbols. Okay, so somebody else said you can run question mark and then a symbol.
Yeah, but I was a little bit worried about Pluto.
But yeah, so that doesn't not actually tell you the information for all the symbols, so that needs to be fixed.
Yep, that would be good. Okay, so
great.
All right, composing functions in math, composing functions in computer science. I kind of already almost said that whether you could actually name the composition in that language, right? And so just as I showed before, we can name the sine, circ, cosine function, and that's something that is a first-class object that you can play with. Oh, but here, Charles,
when I put for the approx, I don't see where it tells me how to type it.
It doesn't. That's what Dave was saying. It doesn't. So, I mean, I will just do this by saying for approx, you can type /approx,
right,
plus tab. Yeah. So.
Gotcha.
Right, but yeah, it's not in the. It's something we need to fix. That would be good. So,
cool.
so here's a bigger point that is something that a lot of people talk about these days, a bigger computer science point, which is the composition of software at higher levels. And there's a lot I could say about that. You could read what I wrote, but in a world where everybody's in a hurry and everybody writes code to do the job that their boss tells them, their supervisor, their boss, their thesis advisor that says, get this thing working, get it to do this, that, and the other. If somebody else goes and writes another function, it's fairly rare, I think it's fair to say, that the two functions, even if they conceptually work together, they may not work together. For example, you could have a simple function that puts strings together, okay, but maybe doesn't put numbers together, or right. So with having software compose is a really big deal. The applications in computational science these days that everybody wants is that you have a big code, maybe written over many years. And now what you'd like to do is surround it with an optimizer. You want to just fiddle with one parameter. It might be solving a complicated differential equation on the inside. It could be doing all sorts of things. But all you want to do is change alpha. You don't really want to care what's on the inside. A lot of code will break. If it doesn't break, we're in the happy position of saying that it's composable, that the optimizer is composable with the code that's on the inside. Sometimes people want to do a machine learning neural network and have a differential equation on the outside, you see. And so all of these sorts of things are, what people want to do these days. And really what we're looking for, and this is what the Julia community is striving for, is for, in some perfect world, everything is composable with everything. That's sort of the dream. And Julia sort of is getting there to some extent, where the person writing this code over in Mongolia and this other person writing this code in South Carolina, it just works together, even though these people didn't plan for it. They didn't shake hands. They didn't write this. They didn't write a spec for it to work together. It just does. And when that happens, that's sort of a very happy position for composing. So the idea of composing, whether we're talking about composing a single function of one variable or multivariable or software in general, it's the idea that you could do the one thing and then the other thing, right? And it just goes all the way through. Okay, so let's, let me skip over this and let's talk about, this is what I said I would talk about in a minute. I'm going to run out of time, but let me at least get in the definition of linear transformations. And so you've already heard me say that when you see a matrix, I would like you not to think of a table of numbers anymore, if you can help it. Here are a few kind of definitions of what a linear transformation can mean officially. So yeah, you always have to have 0 going to 0, but other than that, the rectangle grid lines becomes a lattice of congruent parallelograms. That would be sort of a perfectly good operational definition. Another sort of algebraic operational definition is, it's sort of backwards from the way I wish people would think, but the definition is linear if it could be defined with a matrix times vector. Okay, here's a sort of scaling and adding definition, which will be combined in a minute to become the true mathematician's definition. So if the scaling and adding definition says that if you take a vector and scale it and then transform it, that would be the same thing as if you first transformed and then scaled, right? And similarly, if you transform the sum, this would be the sum of the transforms. Okay, and these two combined, you actually can combine them into one thing. And this is sort of the usual mathematical definition. We say that we call this a linear combination, as we saw in an earlier lecture. We say that a transform of a linear combination is the same linear combination of the transforms. If this is true for all numbers C1 and C2 and all vectors V1 and V2, we say that this is linear. And so getting back to sort of Charles's question, this property would not exactly hold for the perspective transformation. So this would actually fail. Okay. So mathematicians love to start with this definition and then grab a matrix afterwards, okay? And I'll just say, no, not that matrix, but that was a good movie. But if you have the transformation first and you don't have the matrix, you can always get the matrix by looking at t on the 1, 0 vector, that's that horizontal vector in the x direction, and then t on the vertical vector on the y direction, because this will be the first column of your matrix, and this will be the second column of your matrix. And once you know those two columns, you can get t anywhere by just doing linear combinations. All right, I'm going to stop here because I don't want to go beyond 2 o'clock. I probably already used up my microcentury. So I'll just start next time with the question that, let me at least ask you this question. You've all learned how to multiply matrices. If you've taken 1802, you've seen it there, maybe you saw it somewhere else. Did you ever stop and wonder why matrix multiplication has that weird definition? Like, you're adding matrix addition, you just add all the corresponding elements. Why can't matrix multiply be multiply the corresponding elements? Like, who said that matrix multiply was so complicated? Did you ever ask? Or maybe you're all such good students, and when your teacher told you this is how you multiply matrices, you just listened. Okay, well, if you've never thought about it, or even if you have, I'll start the next lecture by talking about why matrix multiply really is what it is. Okay, how did it come out to be this important thing? Okay, all right. So I'm going to shut up. I'm going to say goodbye to the people out in internet land, and the MIT students can stick around if they like, and we can chat with them for a little while. Or can I do that? Or let's see. Yeah, I'm going to stop the live stream. All right. So goodbye, internet land.